Good afternoon and welcome everyone. Thank you for joining us for the overview of HI Data Tool free webinar. I'm NEMA from Hydraulic Institute and Pump System Matters. This presentation is brought to you by Pump System Matters. Pump System Matters supports the industry regarding strategic broad-based energy management and pump system performance optimization by providing the marketplace with trainings, tools, and collaborative opportunities that progress sustainability practices into normal business operations. We are extremely thankful and honored to have one of the very knowledgeable and top industry subject matter expert, Mr. Peter Gaydon, instructing the webinar today. Mr. Gaydon is the Deputy Executive Director at Hydraulic Institute. Mr. Gaydon held design, development, and test engineering positions with major pump manufacturers. With Hydraulic Institute, Mr. Gaydon has technical responsibilities for standards, guidebooks, technical regulatory affairs, and certification program. Mr. Gaydon obtained his bachelor's degree in mechanical engineering at the University of Alfred. At this point, I would like to hand the presentation to Mr. Gaydon to begin today's session.
Thank you for the introduction, Nima, and welcome everyone to today's webinar on the recently launched HI Data Tool. So the agenda for today's webinar, I'm going to present a couple slides, and then I'm going to do a live demo. But the demo that I give, there's some slides that you can download from the training site. If you want to go back and review some of the tools and such that I go over. Okay, so our agenda, I'm going to go over the background. I'm going to cover the HI engineering data book, which goes back many, many years, more years than I've actually been alive. And then most recently, what we've published as phase 2, the HI data tool, and phase 1 being what we had branded as the HI data library. So I'm going to show the progression, and I'm going to give an update on the HI data tool, what it covers, and I'm going to highlight a lot of the key features that we added that I think are pretty cool. So going back, if you've been around anytime, you may have seen a book that looks like this. This is a picture of the Hydraulic Institute Engineering Data Book, first edition. There's actually versions that precede this. If you're looking at my camera, this is the pipe friction manual, which was actually published before the engineering data book. And then that was absorbed into the engineering data book. And this was designed as a resource for system design engineers and pump engineers, and it had a one-stop shop for all the information you needed: characteristics of fluids, fluid flow, pipe material, flange material dimensions, some other useful information. And this book, published in its second edition form, is still available and for publish or for purchase in hard copy, but and going through the sections that are covered and what we're going to review, how we address these in the data tool, we tried to maintain some of the same sections, but make it freely available to the public and kind of the next generation. But, section 2 covered characteristics of fluids, properties, specific gravity, absolute vapor pressure, etc., viscosity. Then section 3 was fluid flow, so how friction loss occurs in pipes and what factors contribute to that. The equations, the friction factors, the Moody diagrams, and calculation methods. Then section 4 provided the pipe and flange materials. So what are the dimensions of the pipes? And then section 5 had useful information, some conversion tables, other things related to altitude, information on mechanical friction in line shaft pumps, So about 5, 6 years ago, we looked at this engineering data book and we said, well, how can we make this available for the next generation of system designers and pump engineers? And we took a survey, and the survey had about 200 responses. About 2/3 of those were domestic U.S. Responses, and about 1/3 of them were international. And what the survey said was that folks wanted this digitally, they wanted it available on all devices. And they thought having some tutorial content in addition to the tables would be good, functionality on searching. So that was kind of feedback on the format. And over here on the right-hand side was the content that people were looking for. And the last 4 bullet points, you'll note, was really content that could be supported by the data book, but was not necessarily included in it because you can't really have calculators in a hard copy version. So we strived to address these in phase 1 of our update, which was going from the engineering data book to the engineering data library. So in 2021, we published the free site edl.pumps.org, and it addressed a lot of those survey concerns. But then, we continually improve the way we develop content is through committees, and we're always reviewing and trying to meet the market needs. So we went in and we launched here in 2024 the updated version of the site. And the updated version of the site includes a lot of interactive tutorials and a lot of calculators. And so it's more than just a data book. It's more than just a library. We updated the branding on this to the HI data tool. So right now, if you put in datatool.pumps.org, you'll get our current site. If you are a user of the old engineering data library and you were used to using the edl.pumps.org URL, that will land you on the updated data tool site as well. And so now that I've given kind of some of the history, I'm going to go ahead and go through a demonstration of the site. So this is kind of the landing page for data tool at datatool.pumps.org. And what I want to illustrate on this page, it provides some information about the site, how it works. And so over here, we've got a menu bar. And really, this top menu bar will allow you to look at a bunch of things on our main website, pumps.org. Okay, and it also allows you to contact us if you want to provide some comments about the data tool. Okay, but the navigation bar over here on the left-hand side, you'll note that this follows a section structure similar to that data book that I showed. And in the most recent release, we updated this so it has a expandable menu. And the section here that I've just expanded is brand new in the updated data tool release. Additionally, for all the calculators, we have a quick access calculator bar here at the top. Okay, but before getting into the sections and showing you some of the new content that's in there, one important thing to know about the data tool is that it is US and metric units. So up here in the top right, if the page that you're on has multiple units relevant, this click option will show up on the top right, and you can switch between US and metric units. So what you'll notice right here, since I clicked US units, you'll see it says this page is currently set to US customary units, just to show you how this will work when we're on the remainder of the pages. Additionally, there is a search functionality for the entire data library. So, for example, if I put friction in here, what you'll notice is the first thing that it shows you, it says on the page that you're on, there are 2 results, and you can navigate through those. But then it says, okay, within the data tool, where else is that term used? So I could then go to calculators where it is used, and I can navigate through that page. And the nice thing is it highlights everywhere that term that you're looking for is used. So we can efficiently search through the data tool to find what we are looking for. I had covered the US and metric units, but this is an opportunity to look at an example of how we can do that. This is a friction loss calculator, which I'll go over a little bit later, but I could look at US units, and then I would input gallons per minute and feet. But in metric units, I input cubic meters per hour and meters for length. So that's an example of the US and metric units. So another example where that is very prudent is in the fluid properties. So if I was here looking at water properties, you'll notice, my water tables are in metric, but I can then toggle them and get the US units for the tables. Another notable improvement for this edition of the data tool is that all of the tables are scrollable now. In the past version, you had to scroll the page, so the pages were very, very long. One of the other updates in this launch of the data tool is that we've added a definition and resources section. And so we have acronyms and definitions that are used within the data tool. So this is not a global set of acronyms and definitions. Yeah, we may do that where we want to define more terms and publish them, even if they're not used in the data tool. But right now, we're defining the terms that are used in the data tool and the source for that definition. So if you're interested in the document where that definition is sourced from, you could link out to it. Or where it is used, I could click on pump principles and it'll take me within the data tool where that term is most used. Now, additionally, within this new section, feedback was that it would be good if we had basic descriptions of all the pump types for nomenclature. And what you'll notice is at the top of the pages, we have an index. So I could say, okay, I want to look at rotodynamic vertical suspended pumps, and it'll take me down the page to those where we've included, the family tree, but then we can go down and say, okay, a VS2 pump is vertically suspended, single casing, discharge through column, volute type. So right here, the VS2. And if you needed more information about the pump nomenclature, you could go to the applicable references. And we've included global references for the Hydraulic Institute documents used and references, as well as external standards that are utilized throughout the data tool. So the ANSI ASME standards, the AWWA standards, ASTM, NIST, etc. So you can find all the references. Because one of the real important things that we wanted to address is that, you know, people use Google to find a lot of resource material. And now that we have AI, you know, they use AI tools. Well, how do we ensure that the content that our engineers are getting is vetted? And so we thought it was really important as a Hydraulic Institute to follow our normal processes of peer-reviewed, committee-led content development to make sure that it's product-neutral content and it's consensus content. And anything that we put in here should be backed up by a reliable source. Okay, so you can trust the content and the reference material that you're going to get from the data tool. And then additional resources if you want to navigate other Hydraulic Institute resources. We've listed them there in this new section. So within the first phase of this, when we published in 2021, we put in the pump fundamental section because that was one of the survey items that said, hey, we need some fundamental content that, you know, new people can find on Google that's reliable. We can send our engineers there to kind of prime them. So we added these sections, but in phase two, you know, I'll scroll through it. I'm not going to go through all the content, you know, but it's tutorial information on, you know, system curves, etc. And we've got some worked examples if you want to go through some practice calculations. But one of the updates we did is we wanted to make some educational demonstrators to show how, like, a system curve or a pump curve or the operating point is going to vary, and show it generically. So for instance, if I change the pressure in this tank, in this system, and I increase that pressure, the static head is going to increase. If I lower that pressure, the static head is going to decrease, and my overall system curve is going to increase or decrease. Now, if in this piping section, if I, you know, increase the friction loss for the major and minor losses, right, I'm going to have more friction head. And so the static head didn't change, but the friction head increased. So we can use this as a interactive tool to teach newer people to the topic how changing things in the system are going to affect the system curve. Like if I increase the level of the supply tank to the pump, my static head is going to decrease. Okay. But where this really comes together is when we look at section C, where we have the combined pump and system curve, right? So we can scroll through the tutorial information that explains pumps and system curves. But here we show, okay, now we've got a pump curve and a system curve, and we can change the speed of the pump curve, right? So this is our base speed curve. Now we're operating at 110%. Our operating point moves from here to here. Then we could add, you know, friction losses, and we could see how now that operating point would move again, flowing head. So again, there is a kind of visual tutorial way that we can demonstrate how the system hydraulics are going to change as we change how the pump operates. And, you know, scrolling down through this section, we have additional demonstrators to illustrate how, for example, a control valve and control head could be viewed in the system. So if I just set this at 100% speed, so we're not looking at pump speed, and I put my valve at 100% open, essentially that valve's not doing anything, right? But here, if I looked at a valve setting of 50%, this is my base system curve here in red without that control valve. And then this green representation is the head loss across the valve. So by throttling that valve, I move the operating point from here to here. We haven't necessarily, we could look at it as changing the system curve, but here we're showing it as we've really just dropped that additional head across the valve. And we're showing an illustration of that. And likewise, we have some additional demonstrators that we've added for parallel pumps and the effect of adding parallel pumps and variable speed with the parallel pumps. So again, you can play around and look at, I think, up to 5 identical pumps in parallel and kind of just show how the system hydraulics and the operating point would change. So those were the primary updates in the pump fundamental section. We made some minor updates in the pump principles, mostly graphically within this section to show the impeller types, illustrate cavitation or why cavitation happens. So some modest updates there, and we added a short tutorial on submergence as well. So what is submergence, and where can I find some more information? Then within the fluid properties section, we didn't make many updates here other than in the tables, how you can scroll in the tables. That is different, and the presentation of the tables have been updated. So nothing I wanted to show here specifically. Within the fluid flow section, this is where we present the methods for calculating frictional head loss. The main update here is that sections A and B have some of the contents been swapped, so that really section A covers the major losses and how to calculate those for pipe frictional losses, and then B really will cover the minor losses for the fittings and how you can approach those calculations. Now, we elected not to cover in detail losses with other fluids because it's covered in our frictional loss calculator, which I'm going to demo here at the end. Now, section, this pipe, flange, and motor dimensions section. This is completely new for this release. We had this data in the back end, but we didn't publish it. We've decided to publish it in. We had it in the back end because we used it for all the friction loss calculations, which I'm going to demo. But we've gone in here and we've published the standard dimensions, based on the standards that they're from. So when we do the frictional loss calculator later, you'll notice that I can select standard pipe, and it will refer to these sections. So we've added plastic pipe as well. We got steel, stainless steel, ductile iron, non-ferrous, and we put in some of the plastic PVC pipe, and in that there's several tables that you can expand to look at that data. The flange dimensions, they operate in a similar fashion where you can expand the class that you're looking for and look at the standard dimensions. And another new update for this section is the motor dimension tool. So you can go in and say per which NEMA standard you're looking for, and you can get the standard motor dimensions. And then the JM, JP, so the close coupled pump motors down the list. So there's lots of good relevant information there. Now on to the calculator. So as I mentioned, we've got the calculators listed here. They're also at the top for quick reference. So unit conversions were in the initial release, but in this release we've made several improvements so that we have more dimensions available to select from. Okay, and we've included an abbreviation and unit in case you're not familiar with the abbreviation that's there. It will show you for each one of these what it means. So if I click to the flow volumetric now over here, it has the abbreviation and unit. Okay, so this is a very robust unit conversion. I would bookmark it. I use it all the time. And then if you have the units, you can just swap them. So you go from 1 gallon a minute to cubic meters per hour. So that's a nice feature. So that's the unit conversions. And so these are all developed based on the NIST standards. So we've put that source there as well. So we also have a viscosity conversion tool. We cover viscosity in fluid properties, so you can read about viscosity, what it is, typical units. But we wanted to create a conversion tool that would go from kinematic and dynamic viscosity if you were doing that. So it incorporates the specific gravity of the liquid. So you can go from 1 centistoke to, or excuse me, 1 centipoise to what would it be in centistokes if I had a specific gravity of 1.5, and we can then see what the centistokes would be. You could show the calculation steps to get there as well. So that's the kinematic and dynamic viscosity conversion tool. The pipe friction loss calculator. So this was probably the biggest thing that we developed in the initial launch, but we did improve it for this phase 2 launch. But the way that it works, so instead of here in this fluid flow section, so instead of going into this section and looking up the friction factor and based on the Reynolds number and the Moody diagram and all of that, this calculator tool allows you to select the pipe. So I could select steel pipe, and then it allows me to pick the nominal diameters based on that standard. So I could pick 5-inch. The identification, whether it's standard, or the schedule or the wall thickness. So I could pick standard schedule 40. And it inputs the dimensions that it's pulling from those charts. Then you could put in the flow rate that you have through that section of pipe. Let's say it's 1,000 gallons per minute, and I've got 1,000, let's say 1,000 feet of pipe. If it was not water, you could put in the viscosity, either kinematic or dynamic. Let's say it's dynamic. So I could put in, say it's, the absolute viscosity is 100 and my specific gravity is 0.8. And it will do the friction loss calculations for you. One of the nice features about the friction loss calculator is that it gives you for flows above and below the flow rate that you entered. And it shows the velocity for that flow rate. So what's highlighted is what we put into the table. It gives you the velocity head, which is a useful value to have. The Reynolds number, whether the flow is turbulent or laminar, the friction factor that it gets from the Moody diagram, and then the calculated head loss. Now, if you wanted to compare other diameter pipes to this, right now we don't have a compare function, but you could just duplicate the browser and say, okay, I want to compare what it would be with 6-inch pipe, standard schedule 40 with that same value. And you could say, okay, well, 6-inch it'd be 150 foot of head loss, but with the 5-inch, it's 360 feet of head loss. All right, so that's the pipe friction loss calculator. The next tool that I'll highlight is if you use vertical line shaft pumps, we had a methodology in the data book for calculating the mechanical friction loss for line shaft bearings. And that was in accordance with AWWA E103. So we had, published a chart in the data book that was worked on by pump manufacturers with the AWWA. And what we did is we digitized that nomograph and made a calculator out of it. So you don't need to go to the chart and figure out the losses. So you can, based on metric or US, if it's metric, it'll say, okay, shaft diameter is between 12 and 175 millimeters. And then in US, the corresponding. So if I had a 5-inch shaft, and let's say it was a 1,000-foot pump length, L. So this is the column, length that we're showing here. And from our standards, that's called the pump setting length. And then the rotational speed, whether it's a enclosed line shaft with a flooded tube or not. And it gives you the mechanical friction loss per 100 feet or, the total. So horsepower per 100 feet was how it was always presented in the graph, the graph that was presented. But we're then calculating it based on the actual length. One of the other notable items that we added in this release is tank volume calculators. So we have a tank volume calculator for horizontal, vertical, and spherical tanks. Okay, and so I'll just do the vertical one quick. You can pick the bottom type first, so hemispheric. I'll pick the top type. You can pick whether it's flat, hemispherical, or 2-to-1 elliptical. What units you want to use? So I'm going to say inches. And so what's my tank diameter? D. So I'll say 100. What's the A length? Say 100. And then it asks you what the fill depth is from the bottom, which is H. And I'll say, let's say 50. And you can calculate. And what you get is that's 22% of the volume. And it gives you the total volume in the units that you used. okay? And it tells you the volume in each piece. So the volume in the bottom, and then the volume in the cylinder, and the volume in the top head, okay? And then the total liquid volume. So if I put this up to 100, then we can see, okay, I've filled up more than just the bottom portion. It's now, into the cylindrical portion. Now, if I change the head type, my image also changes. And if you just want to look at what the equations are for each of the components, we give you those as well if you want to do your hand calculations. So then the last tool I want to go over is the effect of elevation on atmospheric pressure. This calculates the effect of elevation above sea level on standard atmospheric pressure. So it presents the standard at sea level in this column, and then at the elevation you put in. So if I put in 5,280 if we're in Denver, I should expect a delta of 5.3 inches of mercury, 2.6 psi, 0.2 atmospheres, or 6 feet of water. Okay. And then if you want to look at that in other units, you could click here. But essentially, a lot of times, if you're looking for your site pressure, you can Google and get it from the Weather Service, and they'll say, the pressure is 29.9 inches of mercury, and that's corrected to standard sea level for your location. And then you need to correct that based on your actual elevation. So this is a useful tool if you want to determine the effect of elevation on your net positive suction head available. For instance, here you would have 6 feet less of NPSH available than if you were at sea level. That concludes the demonstration on the calculators. If you want to keep up to date on what the updates for the releases are, we do have that listed there. And before I open it up for questions, I do want to give a special acknowledgement to our committee members that really contributed to the updates. This probably took 2 or 3 years to work on the updates, and a lot of time and effort from these folks, really great subject matter experts in reviewing and making sure everything was correct. One more thing that I want to highlight is, as you use the site, we always encourage feedback. So you can go to the contact us. That will take you to the contact us site. You can put it in through a support ticket, or you could enter it in down here and put your information in and send us a comment on anything that we should address in the future, or anything that you may have a question about. Well, thank you, everyone. I appreciate the time.
Thank you, everyone. Thank you for joining. Thank you for teaching, Pete. And have a wonderful rest of the day.